So in order to do these derivations, let's go back to table 9.2, where for different shapes you had different areas. See, there's a mistake in this unit over here, should be meter square. And we looked at I and Z values, the second moment and the section moment. This unit is also meter cubed. So when we go from bending to torsion, mainly instead of the moment I, you deal with moment K, and in an analogous situation to moment Z, you have moment Q. And these can all be derived for various shapes. Just like Z was I over Y max, Q would be K over R max, where R would be the maximum radial distance from the neutral axis where torsion is applied. Effectively, instead of tensile strength, come across shear strength as the material property of interest. Shear strength and tensile strength are related to each other for in most cases. Roughly, shear strength is half of that of the tensile strength. And so typically in a handbook or a material database, you're more likely to come across tensile strength compared to shear strength. And so accordingly, you can estimate the shear strength in this case, which is of importance for a torsional loading. In that manner, you can begin to estimate shape efficiency factors for torsional loading, right? Whether it was a stiffness limited design or a strength limited design. And instead of these two familiar terms that we have seen for the case of bending, you will come across these two new shape factors that are specific to a torsional loading situation. And depending upon whether the design is stiffness limited or strength limited, you can come across these two options over here. Otherwise, the functional form remains the same. Let us go ahead and use those two terms for a torsional loading situation for a shaft. It should support a torque T star before failing and should be as cheap as possible. So we have to minimize the cost. And in order to do that, basically, we will have to minimizing the shaft per unit length, and we have to look at saying that this is the material index, right? Where it's very similar to what we looked at for a strength limited design for bending, except because of the torsional loading, the shape efficiency factor is going to be different. Because we're minimizing cost instead of mass, the cost term is the cost per unit mass is present in the denominator for this kind of a loading scenario. In order to derive that particular material index, let's pay attention to the term phi t, right, under failure, which is 4.8q divided by a raised to 3 over 2. So what we will do is we will use this parameter and then eliminate a from the equation, and then we can derive come about this particular scenario. So if you break down that particular design problem into what is a function, you need to get a cheap shaft. The constraint is that the torque that it should take before failure should be at least T star. The length is specified. You want to minimize C, and you can freely choose any material you want, and A can be varied, right? Shape can be changed. So to come to this, our objective of minimizing cost, C, is what is the cost of this geometry? It is A times L, which is a volume, times rho, that will give you the mass, and cost per unit mass will give you the cost of this component. The constraint is that the torque on the beam should, which is proportional to this shear stress of the material, should be at least T star. So capital T is the failure torque, tau F is the shear strength of the material, Q times tau F is the torque that can be supported by the beam at failure, rho is the density. So we had seen that we had to bring the shape factor into this equation to be able to find a material index that takes into account shape, the cost of the material, and the mechanical properties of the material. So that is where, if you look at the equation where you can replace Q by 4.8 divided by phi f times a to the power 1.5, right? Because phi f was defined as 4.8 times q divided by a to the power 3 by 2. So by using the shape factor here, we can replace q in this equation, and now a can be replaced, right, because the free variable, by rearranging these terms of over here. So basically the equation for C comes to be the product of a loading term, which is defined by T star, the maximum torque that the beam has to carry, the geometrical term, which is given by the length L, and the material related term, which depends upon Cm, rho, and the shear strength of the material and the shape of the material. So you can minimize C by maximizing the reciprocal of this term within brackets. Because the tensile strength is more readily available for a material than shear strength as a data, if you approximate tau f by sigma f by 2, you basically have a term that looks very similar to the material index that was used for bending, except that the nature of the shape efficiency factor is specific for this particular loading condition. So it's different from phi b. What happened to this 2 over here? Basically, it got lumped into this constant inside of. So moving forward, what we will look at during the next design exercise is scenarios where how do you apply this considerations for more complicated and large structures compared to simple I-beams or tubes or columns or square cross sections, for estimating shape efficiency factors to say, is this bridge that was built 1,000 years after this bridge, is this better at carrying certain loads and having large spans, or what changes over time in terms of bridge construction? Another factor to look into is here are a bunch of different interesting shapes in the microscopic scale as opposed to the macroscopic scale. In all these cases, whether it is bone, whether it's a shell, whether it is a leaf, they all can handle different amounts of strength. For instance, a coral can be able to survive in the depths of the ocean and handle all those pressures, right, which offshore structures find hard sometimes. How does a light coral achieve that capability? These are some kinds of things. How do certain fish, how do certain sponges, right? How do they survive the depths of the ocean and the stresses involved? We can again look at ways in which we can use this shape factor term, and by virtue of making these interesting shapes, how failure strength and how stiffness can be addressed by these organisms. This is the focus of the next design exercise. During the next class, we'll continue our considerations of shape selection, in particular looking at how to use some of the features in the CES EduPack software to be able to combine material selection with shape selection. So we'll continue the conversation in the next class.